So we've already investigated a series circuit. Let's review the equations that go with that. First off, I've got my voltage. My total voltage is going to be equal to the different voltages in the system. My total current is going to be equal to the current at any point in the system. And then my total resistance is going to be equal to the addition, the sum of all the resistors in that circuit. A parallel circuit, instead of having all of these things happening right in a row, it says, what if we took them all and we had them happen at the same time? So to draw a parallel circuit, I'm going to draw a power source. I'm going to draw one resistor. And then connected in the same way, I'm going to draw another resistor. Do you see that difference? In a series circuit, they're happening one after another. In a parallel circuit, I've got them happening at the same time. So if the current wants to flow, if the electrons want to flow through here, they're going to flow out of this, and then when they hit this junction right here, they're going to go in both directions at the same time. So they're going to split up. It's like Scooby-Doo and the gang, splitting up to go solve a mystery. Fred goes one way, Shaggy goes the other. So, as this current flows through here, we're going to get some different rules. Because if we think about it, what voltage are these both going to see? Well, at the same time, in a series circuit, we saw different voltages. We saw a sum of voltages because this one used up some of the potential energy, and then whatever was left got down to this guy, and he used up the rest. Well, this one, we're not going one after the other. And so, our voltages are going to get spread out between these two equally. And in fact, our voltage is actually going to be equal on both of these branches. That's what we call this. We call these separate branches. So this is my V total, and this is V1, and this is V2. Then my V total is going to be equal to V1, which will be equal to V2. It's going to be even. It's going to be just like the current was in a series circuit. Well, what about the current? The current in a parallel circuit is splitting up. And so if you think about this in terms of like a system of piping that water has to flow through, if I want to have two separate pipes flowing right here, and they both connect to one main pipe, what has to be true about that main pipe? Well, it's got to be bigger. It's got to carry the current for both of those smaller pipes. So in a parallel circuit, my total current is going to be equal to the current added together in each of these. So we see that our rules for voltage and current just switched. But what about resistance? Resistance is going to be a little more complex here. And the reason for that is if this resistance is really small and this one is really big, if we think about it, electrons can try and move through this one. They're going to hit a lot of resistance. They're going to try and push through, and it's not going to be that easy. But they can just go over here and move through easily. It's like trying to go to a store and there's a front entrance and a side entrance. And it's Black Friday and there's 1,000 people at the front entrance trying to get in, but no one knew about the side entrance. So they're all trying to push through, and you can just go to the side and get through just fine. And so because we have a lower resistance over here, our current over here would be a lot larger. So how do we factor that in? There's a very tricky bit of math that goes with it. The total resistance in a parallel circuit is going to be the reciprocal of the reciprocal. It's a tough concept. So the reciprocal, that means the 1 over something. So that's our first one, first reciprocal. Then our second reciprocal of each resistance. that is how we find the resistance in a parallel circuit. Now, let's do a sample problem. I've got a parallel circuit here. Voltage 1, 100 volts. R1, 1 kilo ohms. R2, 5 kilo ohms. We want to find the total resistance, the total current, and the current through each resistor. So let's apply our rules right off the bat. First, let's find our total resistance. So in order to find this, we're going to plug our resistors into this formula here. So that's going to be RT is going to be equal to 1 over the addition of 1 over 1,000 plus 1 over 5,000. Now I encourage you to go through the math, look at what 1 over 1,000 is, plus 1 over 5,000, just look at that answer. And if we look at those together, we'll see that the reciprocal of that is slower than both of them. The whole idea is that whatever resistance we come up with has to be lower than either of these possibilities. Because even if this resistor gets too crowded, the 1,000 ohms, the electrons still have the other resistors that they could go through. So it's like there's actually less resistance. So doing this math on our calculators, we get 833 ohms. So we can see 833 is less than either one of these. So our total resistance in a parallel circuit is always going to be less than the resistance of any of our components. 833 ohms. Okay? So now we should be able to see this. Let's prove it by using Ohm's law. If I take my voltage and divide it by my total resistance, I'll get my total current. If I take my voltage and divide it by my individual resistors, I should get individual current that should add up to my total current. So let's go ahead and do our totals first. I've got 100 volts divided by 833 should be equal to it'll give me 120 milliamps. Okay, now my individual resistors, 100 divided by 1,000, what is that going to be? That'll give me 100 milliamps. Alright, and then I take my 100 again, my voltage divided by my R2, which was 5,000. Which gives me 20 milliamps. So, to check my answers, all I have to do is take my current and make sure that the addition of my two currents equals my total. So, 20 plus 100 equals 120. So everything checks out.